All right, let's get started with question 30 here. The equilibrium equation shown below represents a reaction that produces hydrogen gas for the use in the manufacture of some fertilizers. Carbon dioxide plus methane plus energy brings us to get carbon monoxide, 2 moles of it, and 2 moles of hydrogen gas. Which of the following observations would not be an indication of a system that has reached equilibrium? A, a constant mass, B, a constant pressure, C, a constant temperature, or D, a constant number of gaseous molecules. Now, this is a bit of a definition question. Do you understand what equilibrium means? Equilibrium means that the rate of our forward reaction and the rate of our reverse reaction is equal. It doesn't mean that we necessarily have equal concentrations of products and reactants. In fact, probably not. But it does mean that the overall concentrations are not changing. And because the overall concentrations are not changing, there will be a constant mass, there will be a constant pressure. If we changed the temperature, we would change the equilibrium, and there will be a constant number of gas molecules because the concentrations remain even. So all of these at first glance seem like they would be an indication of a system that reached equilibrium. However, one of these is true of the system before it reached equilibrium, and that's a constant mass. This would be true of the pre-equilibrium state. So if you mixed together your carbon dioxide and your methane, and then you were measuring the pressure, the mass, the temperature, and if you could, the number of gaseous molecules, you would see that the mass was the same at the start as it was at the end. It never changed. So this would not be a good indicator that the system reached equilibrium. If you saw that the pressure leveled out, the temperature leveled out, then if it's in a fixed volume using the ideal gas law, you can assume that you have a constant number of gaseous molecules. All of those would be good indicators of a system at equilibrium, but the mass would be the same in the true pre-equilibrium state. So A is not a good indicator of the system reaching equilibrium. Here's a bunch of different stresses that could be applied to the system. And the question says, when applied at the equilibrium above, the stresses that would cause a shift toward the reactants are numbered what? Okay, this is Le Chatelier's principle. And how I usually go about Le Chatelier's principle is that we are going to shift away from increases, and we are going to shift toward decreases in order to reestablish equilibrium. Let's take a look again. We're going to add hydrogen gas. That was our first stress. If we add hydrogen gas, we will shift away. So we'll go up and away. Add hydrogen gas, shift away to the other side. That will shift towards the reactants. So I'm going to put a check mark here. If we add carbon dioxide gas, then this would increase, and we would shift away from our increase, which means we would shift towards the products. So 2 is not it. Catalysts do not cause a shift. There is no shift from catalysts. Removing carbon monoxide. Well, carbon monoxide is one of our products, and we're going to shift towards decreases. So if we decrease carbon monoxide, we will shift towards the decrease. That would be a shift towards the products. We want shifts towards the reactants. If you remove a reactant, however, like methane, then you would shift towards that decrease. So that would shift us to the reactants. Decrease the volume of the reaction container. If you decrease the volume of the reaction container, we will increase our pressure. Just like they have energy in here as a reactant, because that can help us with identifying which way we're going to shift with a temperature increase or decrease, we could put pressure into this equation on the side that has more moles of gas. There are 2 moles of gas on our reactant side, but there's 4 moles of gas on our product side. So I might actually write plus pressure on this side. Because if we decrease the volume, then we're going to increase the pressure. And we will shift away from an increase, which means we are going to shift towards the side that has less pressure to try and equalize that. So that would actually cause a shift towards the reactants. So 1, 5, and 6 would all cause a shift towards the reactants. Next question. A technician put 1 mole of methane and 1 mole of carbon dioxide in an empty 1-liter reaction container. The container was sealed and the system was allowed to reach equilibrium at 1,200 Kelvin. At this temperature, the value of Kc is 3.3 times 10 to the 10. Okay. Which of the following sketches best represents the progress of the system as equilibrium is established? I'm just going to write on the side what Kc is. Kc is our equilibrium constant, and it's going to be our moles of our products to the power of their coefficients over the moles of the reactants. Now, this here, concentration of our products to the power of their coefficients. I said moles. Concentration of our products to the power of their coefficients divided by concentration of the reactants. It's the same equation here. So there's a coefficient of 2 with the hydrogen gas and with the carbon monoxide. So our Kc value here is going to be carbon monoxide concentration squared multiplied by hydrogen gas concentration squared divided by carbon dioxide concentration times methane concentration. That's how we're going to get our value of Kc. We also know that this is equal to 3.3 times 10 to the 10. This is a massive number. That's moving this decimal place 10 times to the right, which means if we were going to actually put this into the expression, we have much larger concentrations of carbon monoxide and hydrogen gas at equilibrium than we do of carbon dioxide and methane gas. At the start, though, we don't have any carbon monoxide and hydrogen gas. Let's take a look through all of these different graphs here. Now, for these 2 graphs, A and B, I'm going to eliminate. The reason why I'm going to eliminate them is because we have such a large Kc, we clearly have a much higher concentration of carbon monoxide and hydrogen gas than we do of carbon dioxide and methane. Then if we look at graphs C and D here, graph C shows us that we have a decrease of carbon dioxide and methane that's much larger than the increase of carbon monoxide and hydrogen gas. But because we have a coefficient of 2 for both the carbon monoxide and the hydrogen gas, we know that their concentrations are going to grow twice as fast. So we should end up with a lot more carbon monoxide and hydrogen gas. So D is our best answer. A, if you looked at A and you thought, well, A looks like carbon monoxide and hydrogen gas are growing twice as much than carbon dioxide and methane gas are decreasing. I don't blame you for feeling like, okay, initially A looks like a good answer, but if you're investigating the size of Kc here, we must have a much, much higher number for these concentrations than these concentrations. So this has to go all the way to the floor. But yes, carbon monoxide and hydrogen gas will grow twice as fast in their concentrations than carbon dioxide and methane gas will decrease. In order to calculate the equilibrium concentrations, what equation, where X represents the change in concentration of methane gas, could be used? We're going to build a Rice table for this, where the R represents our reaction, I is our initial concentrations, C is our change, and E is our concentrations at equilibrium. Here's our initial reaction. We have methane plus carbon dioxide that is becoming 2 moles of hydrogen gas and 2 moles of carbon monoxide gas. The initial concentration in this 1 liter reaction vessel from our text box above is 1 mole of each gas in 1 liter, so their concentration is going to be in 1 mole per liter. So we start with 1 mole per liter. We can do 1.0 moles per liter. I should erase that. I'm getting it all bunched up. 1.0 moles per liter of both of our reactants, and we start with no products. Again, as I said in the graph question, because these have a coefficient of 2, they're going to grow by some amount, twice as much as our reactants are going to shrink in their concentration. So we're going to say minus x is our change in concentration for our methane and our carbon dioxide, and plus 2x is our change in concentration for our hydrogen gas and our carbon dioxide gas, which means at equilibrium, the concentration of our methane is going to be 1 minus x, and of our carbon dioxide is also 1 minus x. And the concentration for our hydrogen gas is just going to be 2x because there was nothing to start, and for our carbon monoxide gas will be 2x because there was nothing to start. If we look back at our equilibrium expression here, we can substitute in those equilibrium values into this Kc expression, and we already know that our Kc value is 3.3 times 10 to the 10. So we know that our expression is going to be 3.3 times 10 to the 10 is equal to, well, we'll put our concentration of our products on the top, which are each raised to the power of 2 because of their coefficient. So 2x squared times 2x squared, and then our concentration of our reactants on the bottom, which is 1.0 minus x times 1.0 minus x. Now this doesn't look exactly like any of these, which requires a little bit of math understanding for how we can combine these terms. If we were going to combine these two terms together on the top, then what we would end up with is we would end up with 2x to the power of 4. Picture it as if you had x squared times x squared. You'd end up with x to the power of 4. But none of these show x to the power of 4 on top. And on the bottom, these two are the same term, so they can combine as well to form 1.0 minus x squared. This appears on the bottom of A and of B. Now, if you square rooted this, then you might think, well, then we can get rid of this square on the bottom, but then you must also square root our Kc value. And because our Kc value hasn't been square rooted, then the value that has something that matches the top and the bottom here is B, where here's our concentrations of our products, and here's our raised to their coefficients, and here's the concentration of our reactants multiplied by each other, which is where that squared comes from. I'm going to stop the video here, and we'll continue on another video.